Hello, everybody. I am Gina Taschetto. I'm a PhD student at the University of São Paulo. In fact, I feel the pressure of speaking right after one of my supervisors. Osvaldo is my supervisor at USP. He just gave us a wonderful talk. And I must say, I feel very honored and humbled for being part of this workshop. I thank the organizing committee, in particular, Haoni, for inviting me. Okay, it's really a great opportunity. Okay, a few things more. My research is funded by FAPESP, so I thank FAPESP for funding me, and it's on observables. Okay, so you can see from the title of my presentation that this talk results from my study that I had not planned to undertake. Okay, it was in the course of writing a historical preliminary for the thesis, intended to be a very short overview of things much studied already by extremely competent scholars, okay, that I noticed some contradictions, and I was led to think that certain important aspects of the standard story that is told about the origin of quantum theory simply fail to make sense, okay? And with that in my mind, I simply couldn't control myself. I could not stop digging until I made sense of the whole thing for myself in my head, okay? And for that, I did not go through detailed archival studies. I'm stuck at home for over a year now. I do not even have access to a library. But the fact is that detailed archival studies are not necessary for this. Simply by carefully reading the well-known papers and the well-known books, okay, all available online, I became convinced that the standard story of the birth of quantum theory, of how it appeared and when and why, it's simply wrong, okay? And I want to share with you today the specific form of my conclusions, at least part of it. I won't be able to tell you the whole thing. But I understand that some of them may sound very controversial. So it's really great that I have outstanding physicists and philosophers of physics, historians of physics listening to me today, outstanding intellectuals listening to me, because I'm very much willing to tell me where I go wrong, if I go wrong in my analysis, because I really want to know if I got things right. I really want to know if I managed to think things through correctly, okay? So I really look forward to your criticism. All right, good. That being said, we can get on track. I open my talk with this quote because I think it captures well the fact of how it can be that after over 100 years of its birth, the story that is told about the origin of quantum theory is myth. Okay, good. All right, so to set the stage, I often hear people quoting Jeremy Butterfield when he said that one cannot underestimate the value of hearing something one already knows. So I will begin by telling you a few things you already know, okay? Let's go back to the late 1850s. When these two gentlemen here, Kirchhoff and Bunsen, they laid down the basis of what they believed would be an extremely powerful tool of chemical analysis. And history proved them right. Spectroscopy, okay? So by investigating solar spectra and the spectra of various elements, Kirchhoff noted that the relative intensity of emission and absorption of radiation obeys a general law, okay, that goes like this. So the ratio between emission and absorption of spectrum is a universal function. We call this universal function K in honor to Kirchhoff, of course. And it's universal in the following sense. It's substance independent, okay? This function depends only on the frequency of radiation. Can you see my cursor here? Can you see it, Haoni?
Yes, we can see.
Yes.
Okay, good. Okay. So this function depends only on the frequency of radiation and on the temperature of the substance that's being considered. Okay, it does not depend on what substance it is. So this is the law then that is said to describe or govern, if you will, radiation and matter in thermodynamical equilibrium. Okay, now on the face of this discovery, the next step was clear, right? One has to find the explicit form of this universal function theoretically, okay? And that, ladies and gentlemen, is what Planck did. You will remember that by definition, a black body is a body that absorbs all radiation that falls on it, okay? So for a black body, alpha equals 1 in this equation, and so K equals epsilon, all right? So Planck's black body radiation law is the explicit form of Kirchhoff's function for alpha equals 1, okay? And it looks like this. Now, the question is how to get to this formula, okay? Now, Planck considered a bunch of harmonic oscillators in thermodynamical equilibrium with radiation in an enclosure. So, note, Planck was not treating radiation as harmonic oscillators, okay? I emphasize this because I see this being said on textbooks. So he was not treating radiation as harmonic oscillators, and he was also not thinking of atoms and treating them as harmonic oscillators, okay? Why harmonic oscillators? Well, you'll remember that it doesn't matter what it is that radiation is in equilibrium with, right, for this problem. So, well, harmonic oscillators are the simplest objects to treat, right? They are always our first try, okay? That's why Planck used them. Good. So again, a bunch of harmonic oscillators in equilibrium with radiation in an enclosure. Good. Now, with respect to the theoretical ingredients that Planck used to derive this formula, it's convenient for us, okay, Planck did not do this, but it's convenient for us to distinguish between the classical premises that he employed. Namely, from thermodynamics, he used the fact that the entropy, the internal energy, and the temperature of a system in thermodynamical equilibrium are related by this equation. And moreover, since the internal energy is an extensive quantity, the energy per oscillator can be written in this fashion, okay? From statistical mechanics, he used Boltzmann's expression for the entropy. And from Maxwell's electrodynamics, he used the fact that a neon that oscillates about its equilibrium position emits and absorbs, on average, an equal amount of energy if its resonating frequency, its average energy, and the energy density of the radiation are related by these formulas. Okay, so we distinguish between these classical premises and Planck's personal twists, so to speak. Namely, this formula to distribute p objects of energy epsilon between n sides. And of course, epsilon equals h ni, where epsilon is the energy of each oscillator, okay? And h is a constant, and ni is the frequency of the oscillator. Let me emphasize again, this frequency is not the frequency of radiation, okay? This is the frequency of the oscillator. And again, Planck was not thinking of atoms. Okay, at that time, people did not really believe in atoms. Really, most people anyway. Good. I also emphasize that Planck did not explicitly make this distinction between premises and hypotheses the way that I'm doing here. Okay. Good. All right. Here's the proof. I will not go through it. I don't think it's necessary. If you want, later in the Q&A, we can come back to this. The thing about this proof is the following. The day that Planck presented it to the German Physics Society is generally said to mark the birth of quantum theory, okay? So it is the presentation of that proof that is said to have set the quantum revolution in motion, okay? And that was on December 14th, 1900. So big deal, right? Now, note that from this statement, an interpretive guideline immediately follows, right? Well, if that derivation, that proof, marks the birth of quantum theory, then to understand the origin of quantum theory is to understand that proof, right? So let's follow this guideline, okay? And for that, I ask you to consider a couple of remarks that Einstein made on Planck's work on black body radiation. So Einstein wrote in 1909, it should not be forgotten that the Planck radiation formula is incompatible with the theoretical foundation from which Planck started out. And he also said, isn't it conceivable that Planck's formula is correct, but nevertheless that a derivation of it can be given that is not based on an assumption as horrendous looking as Planck's theory? So Einstein is saying here that Planck's black body radiation law is true. After all, it was beautifully confirmed by experiments, right? But not the derivation from which Planck infers it. So Einstein is saying that the derivation that marks the birth of quantum theory is wrong. When I read this, I thought, that's weird, right? Because, well, okay, if Einstein is wrong, then we can forget about the whole thing. But if Einstein is right, then this statement appears very hard to understand. Because Einstein is saying, look, Planck's proof is wrong, okay? We must find another proof. And the books are saying this proof inaugurates quantum theory. In other words, Einstein is saying, look, we cannot trust Planck's proof as a source of knowledge. Whereas the books are saying, this proof uncovers the experimental truth of quantization upon which the edifice of present-day theoretical physics rests. And these statements, they appear incompatible with one another, right? They seem that they cannot both be true, because otherwise you would apparently have to accept that Planck's proof is, in a sense, correct and incorrect. It is both right and wrong. When I realized this, I thought, well, that can't be, right? So the way to try to understand what's going on here, or so it appeared to me, was to review what professional historians have said about Planck's work, and then review what people have said about Einstein's critique to Planck, and then compare these things and see what results. And what I found working this way appears to me to be a massive historical oversight, okay, with far-reaching consequences. And I want to try to convince you of that. Okay, good. To begin, what the historians have said on Planck. Fortunately, this is very straightforward because in 2001, Professor Olivier Darigaud, he wrote an excellent paper, okay, very detailed, that's entitled "On the Historians' Disagreement over the Meaning of Planck's Quantum." And in this paper, I found almost all the information that I needed in this respect. So here's how Darigaud opens this paper. During the past 20 years, historians have disagreed over the meaning of the quanta which Max Planck introduced in his black body theory of 1900. The source of this confusion is the publication in 1978 of Thomas Kuhn's iconoclastic thesis that Planck did not mean his energy quanta to express a quantum discontinuity. The aim of the present essay is a comparison of the opinions of various historians on this issue. So, Darigaud is saying that in the history of physics community, everything was fine until 1978. Until then, everybody agreed that quantum theory began with the work of Planck in 1900. And confusion started when Kuhn published this book where he says that Planck did not do that. Okay. Now consider this. So in 1918, Planck won the Nobel Prize in Physics in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. When you look at this, what jumps at you right away is Kuhn's thesis is unacceptable, right? Because otherwise, we would apparently have to accept as a mysterious, inexplicable fact that Planck won the Nobel Prize for something he didn't do. Well, we're going to see that things are actually more complicated, but the fact is that Kuhn's thesis was not very well received, okay? He did not convince most people. And Darigaud, in his paper, he nicely systematizes the different views of historians in this respect in this chart. So there are three theses in the history of physics community with respect to what Planck did. According to the first category, Planck introduced in 1900 the idea that the energy of some microphysical entities, his oscillators, could only take discrete values. And according to the second category, Planck himself did not know, okay, the meaning of his energy quanta. And according to the third category, Planck did not mean to say that the energy of the oscillators varied discontinuously. Okay? He did not mean to break with the dynamics of classical physics. I am not going to pause over this, okay? There's no time for that. And well, that the discontinuity thesis is almost universally held is obvious enough, right? I think I can safely refer to your own experience in this respect. Just let me add that Martin Klein, I think that most of you, if not all of you, are acquainted with his work. He was a very influential historian of physics, okay? And he was an expert on Planck and Einstein, Boltzmann. And well, he was a discontinuitist, as you can see, and he disapproved Kuhn's book, okay? He made this very clear in a book review that he wrote. And no doubt, the weight of Klein's authority had an impact on how Kuhn's thesis was received by the community. Okay, I just like to add that, well, you can see that Darigaud leaves Kuhn alone here in this third category, at least in his analysis, And since Klein is the most powerful discontinuitist, and Kuhn is Kuhn endorses the opposing view, so that Hegel calls this debate over the meaning of Planck's quanta, he calls this the Klein-Kuhn controversy. Okay. Good. So this is, I'm going to say about what the historians have said about Planck's work, and I think, and the upshot is, I think it can safely be said that the birth of quantum theory is as yet an unresolved historical problem. Okay, next, to Einstein's critique to Planck. Now, the thing to be asked here is how the physics community reacted to the contention, to Einstein's contention that Planck's proof is all wrong. And here comes the surprise. Insofar as I was able to verify, no other physicist or historian or philosopher repeated Einstein's criticism. You're going to say, no way that's true, right? A critic as severe as this one, by Einstein, going unremarked, that's incredible. I agree. I mean, it's my point, okay? I think there's evidently a question here of how this can be that suggests that an important consideration in relation to Planck's work, and thereby in relation to the origin of quantum theory, has had a remarkable way of escaping people's attention. Now, I remind you at this point that Einstein's contention, Einstein's critique to Planck, is incompatible with the discontinuity thesis. Because, come on, if the proof is wrong, how could it have introduced quantum theory? It doesn't make sense. But the discontinuity thesis is almost universally held, right? Against which fact, it appears hard to understand how could people have come to agree with Einstein that Planck's proof is wrong. In fact, the lack of engagement with Einstein in this respect suggests further that people did not even notice this, okay? People did not even pay attention to this. But mind you, Einstein never made a step argument of this contention, okay? In earlier papers, as you can see, he just boldly sketches his point. He does not articulate it precisely, okay? And in later papers, he just takes this for granted, okay? So it seems to me that Einstein overestimated the obviousness of his logical considerations. And in view of what it appears to be a great historical oversight, it would repay us to make explicit what Einstein was thinking when he says that Planck's proof is horrendous looking and incompatible with the law itself, okay? And what this understanding does is that it forces to ask questions that takes us to the very heart of the Klein-Kuhn controversy. And what the answer to these questions accomplish is so direct and straightforward as to end the debate, okay, as I see it. I will not be able to go over all this today, but that's the project anyway. Okay, so let's then make explicit now what Einstein was thinking when he was criticizing Planck's proof. And now you're going to understand why I have why I have distinguished the ingredients of Planck's derivation the way that I did. It's because it makes the neatness and force of the following point very obvious. Planck's premises 1 to 3 imply another black body radiation law, not Planck's. And here's the proof. I'm sure most, if not all of you, will recognize equation 11. That's the famous Rayleigh-Jeans law, which Rayleigh derived this in 1900, the same year that Planck derived his formula. Okay, and this formula, it expresses the fact that Paul Ehrenfest, in his famous 1911 book on statistical mechanics, he called this ultraviolet catastrophe, and the expression caught on. Why ultraviolet catastrophe? If you integrate this equation over all frequencies, the integral diverges, right? And this fact contradicts experience. And what is to be inferred from this contradiction with experience is that either premise 10, that's required by statistical mechanics, or premise 4, that's required by Maxwell's electrodynamics, or both of them, are false. Okay, so what the empirical failure of this equation is telling us is that the premises of classical physics were falsified by experiments. Okay, but Planck also used those premises, so his proof can't be right. Okay, this is what is behind Einstein's contentions 1 and 2. This is what is behind his critique to Planck. Okay, now I want to make a few comments. Einstein pointed out that the equipartition theorem leads to Rayleigh-Jeans law in his 1905 paper, in his 1906 paper, in a 1907 paper, twice in 1909, and I think also in 1911 and 1913. Okay, and it was not Rayleigh or Jeans or Planck, but it was Einstein to first emphasize that the empirical failure of this law, of the Rayleigh-Jeans law, poses a problem for physics, for classical physics. Okay, but Einstein does not explicitly state these corolatives in his works. Okay, he leaves these as an inference, and that people failed to make these inferences is clear enough, right? Einstein repeated the argument many times, and yet it took quantum theory years to take off. Bohr's model of the atom appeared in 1913, and Sommerfeld's quantization rules in 1916, many years later. Okay, now it is instructive to ask why people did not get this. Look, at that time, 1900, by that time, statistical mechanics was not very popular. Okay, you will remember, it is difficult for us to get our heads around the fact that people did not really believe in atoms at that time. But, well, those were the heydays of positivism, right? So Boltzmann's theory was not really popular, it was not really studied by many physicists, but of those few physicists that did work with statistical mechanics, many of them believed, and this includes Rayleigh and Jeans, okay, that the equipartition theorem was not universally valid. Now, if you
have 5 minutes now, okay?
5 minutes, okay, I'll try to speak. Is it going to be the end of the world if I pass bits?
No, no.
No? Okay. But I'm almost done. The equipartition theorem, so many people believed, many physicists believed that at the time that the equipartition theorem was not universally valid. Okay, now note that if you grant that the equipartition theorem is not universally valid, then this proposition and these corollaries do not follow, right? Now let's think of that. what comes to my mind when I think of this is one of those famous passages from Quine's Two Dogmas of Empiricism, when he says that any statement can be held true, come what may, if we make enough adjustments elsewhere in the system. Because look, the suggestion that the failure of this formula refutes, okay, by modus tollens in Popper's style, sacred and time-tested classical mechanics, that's a suggestion quite beyond the grasp of people that were trained for centuries to think in terms of Newtonian physics. Okay? In fact, if you think about it, only someone who was already convinced it was time for physics to rethink its foundations would think that, would suggest this thesis. And that Einstein was convinced of this by 1905. We know that well, right? That was the miraculous year. Okay? So in the face of these considerations, it makes perfectly good sense that it was Einstein the first to emphasize that the failure of equation 11 represents a catastrophe for physics. And so it makes perfectly good sense that people were unable to follow Einstein's implicit premises towards C1 at first, right? And towards C2 at all. Okay? And so it makes perfectly good sense, moreover, and this is something that is wrong in every physics textbooks that I had put my eyes on. It makes perfectly good sense that Planck's work on black body radiation actually had nothing to do with the ultraviolet catastrophe. Okay, this is something that Klein makes very clear, very explicit in his 1961 paper, and this is something that all historians agree on. Okay, it's a bit long, but it's worthwhile to read the whole thing. So Klein wrote, was Planck aware of the radiation distribution law, which Rayleigh had derived as a necessary consequence of classical physics? Most authors answer this question in the affirmative and describe Planck's introduction of quanta as his response to the challenge of the crisis brought about by the disagreement between classical theory and experimental results, and by the internal failure of classical theory as expressed in the ultraviolet catastrophe. As a matter of fact, there was no such crisis, or perhaps one should say there was no awareness of such a crisis. All of the work on black body radiation prior to the summer of 1900 was done without benefit of the knowledge of just what classical physics did imply for this problem. So on the face of this, you think, how could Planck have started a revolution to fix a problem that he did not know existed? Okay, now, the myth that Klein's talking about here survives on the assumption that a non-classical law could only have appeared in physics by the pressure of the failure of a classical law. But not only could thinkers in principle had remained within classical physics by making adjustments in the network of statistical mechanics. In practice, they were doing exactly that. Okay, so for a revolution to happen, what is required is conceptual reorientation. And the conceptual reorientation that was important here is manifest, for instance, in this quote from Einstein's 1909 paper, when he wrote, "It should be explicitly noted that the equipartition theorem is an inevitable consequence of the statistical theory of heat. The attempt to question the general validity of this theorem is based, it seems to me, only in a gap in Boltzmann's considerations, which has been filled in the meantime by Gibbs' considerations." This was in a footnote. Okay, and you're going to agree with me that this is very vague, right? He doesn't say what gap this is and how it was fixed. And now that's the this conceptual reorientation that I was talking about, that it involves an element of conviction, therefore a subjective element, is manifest, for instance, in this expression here, it seems to me. Now, you'll be thinking that what I'm doing is I'm suggesting that the actual discoverer of quantum theory, the person that actually started the revolution, was Einstein. And that is exactly what I'm suggesting. But unfortunately, I will not have time to pursue this line of thought. Just let me finish by giving you another argument that shows that, well, it was not Planck. Okay. So one more thing. Let's go back to very quickly to the ingredients of Planck's proof and localize the exact location of the defects in his proof. Okay. So note, one more. Here, here Planck assumes that energy varies continuously. Okay. And here, that it varies discontinuously. And yet, at some point of his calculation, he brings these things together. Okay, that's one thing. The other thing is, if you distribute p objects of energy epsilon between n sites, what you get for the number of complexions is n to the power of p, not this. Okay. So these hypotheses, and let me emphasize again that Planck did not introduce these formulas as hypotheses in his work. Okay. But the fact is that these formulas contradict the electromagnetic and mechanical premises upon which Planck's derivation otherwise depends. Okay, so the proof is self-contradictory, it's inconsistent. That's why Einstein calls it horrendous looking. That's why he said that it must be replaced. Okay. Okay, so the case is made. Now let's see, just to wrap up, let's see where we are. What led us into this discussion was the observation that Einstein's contention is incompatible with the discontinuity thesis. But the discussion that I've just made then gives plausibility to the contention that the discontinuity thesis is false. It gives plausibility to it, but it does not establish that it is false. Because, well, it must be acknowledged that if the discontinuity thesis exists, okay, for over 100 years, and it lingers notwithstanding Kuhn's work, this is so for a reason, right? Well, it will be asked, how can the discontinuity thesis be false if Planck won the Nobel Prize in 1918 for the discovery of energy quanta? And moreover, how could he have arrived at these formulas? From our present perspective, Formula 5 encodes particle indistinguishability, right? And Formula 6 encodes energy quantization. Now, how could Planck have arrived at these formulas if he did not willingly break with tradition? He could not have arrived at them by chance, right? That's absurd. And he could not have arrived at quantum theoretical formulas by thinking with classical physics, right? That's logically impossible. So this suggests that the discontinuity thesis must be true. And moreover, it seems hard to believe that Planck did not note that he was departing from classical physics. It seems hard to believe, moreover, that he did not note the inconsistencies which a very simple analysis like this one that I've made today reveals so easily, right? Planck was a smart guy. So these questions seem to suggest that the discontinuity thesis cannot but be true. And I think that to establish that it is not, satisfactory answers to these questions must be given, right? I think that the problem with Kuhn's account is that he did not worry of this, okay, of these aspects of the discontinuity thesis that makes it appear that it is obviously true. And I must apologize for not being able to establish that today. I'm not happy of leaving things this way. Things may appear now a bit confusing, perhaps mysterious. But I hope I have managed to present arguments that even though, well, if the discontinuity thesis exists, right, and lingers, because it appears obviously true in view of some facts, I hope that I've managed to show you some arguments that suggest that it is not obviously true. Okay, and I must apologize for not actually being able to establish today that it is not true. Okay, that's it. I'll stop talking. Thank you for
Gianna.
for your attention.
We have now sort of 10 minutes for Q&A. And anybody want to do the honors? Christian and Otávio. Christian, please.
Okay, thank you very much. Thank you, Diana, for this great talk. I really, I completely agree that the importance of Planck's work has not been really understood. Still, it's not still understood in physics. We get a very weird story about what happened, and it's not very detailed. But of course, I mean, what you point out is I would like to understand better what you are pointing out with respect to the discontinuity condition, the quantum postulate, basically.
Mm-hmm.
Because of course, I completely agree that all this is kind of inconsistent. But on the one hand, Planck was trying to parameterize a curve, and he added this. He just plugged in this condition in order to parameterize this curve. And as I know the story, he was not very. I mean, he was not very willing to attach a lot of reality to this condition, because he understood clearly that it was a problem. But then, of course, Heisenberg recalls that Planck told his son that that he had made a huge step. So he recognized the inclusion of this continuity condition, the quantum postulate, and of course the quantum postulate is applied by Einstein in 1905, and then by Bohr in 1913 in order to derive the photoelectric effect, the quantum model of the atom, Bohr's model of the hydrogen atom. And then if you go to the first mathematical closed formulation of quantum mechanics, Heisenberg also applies the discontinuity postulate in order to derive matrix mechanics. So why are you saying that this is wrong? This is, or yeah, I want to understand better, more deeply what are your claims?
Mm-hmm, mm-hmm. Yeah, in fact, I understand that in view of what I said, and in view of the standard story that is told, the whole thing looks like a mess. And as I said, there must be presented reasons that explain those questions that I made in the end of my talk, and the questions that you are asking now, for instance. And that would make another great talk.
Okay.
But in fact, if you just unfortunately, to address all these things that you asked, I will have to tell you the history of how things actually happen. For instance, Planck did not parameterize. He did not. The fact is that that Planck was working with radiation theory for years. Okay, and he was using as physical input Weyer's law. Okay. Remember Weyer's law? Viance.
Oh, Vine's law.
Yeah. So his previous work was, and it was a phenomenological formula, Vine's law. Okay, and so what Planck was trying to do, because he was really obsessed in deriving the correct Kirchhoff's function, and the correct Kirchhoff's function was believed to be Vine's law. Okay, and so he was trying to derive that. But then the experimentalists found in February 1900 that there were actually deviations from this law. So Planck's work then out of the sudden lost ground, you see, because all he was doing was trying to derive that law, and he couldn't. And so what he did, he succeeded in writing down a correct phenomenological formula himself. That was a guess. The formula was first a guess.
Yeah.
Okay. And this represents,
right?
And
there he introduced the quantum postulate.
No. So first he just it was a guess. It was not derived. Okay. So
sure. It was a guess. It was not.
It was a guess, and then okay. And then you see there will be many details. Yeah. I'm not sure if I should tell if I should just send you the part of my thesis where I give you all this answer, and everything seems very perfectly clear, I think, because otherwise I would just, But it is as I said, I just started with this thing because I noticed that this story simply didn't make sense. Okay, and I could not stop until I made sense of the thing in my head. And but I can then send you the whole story, that I think it will address all these confusing points of inconsistent pieces of history that may seem to appear. Okay.
Yeah. Thanks.
Because otherwise we'll just talk for another half an hour.
Thank you, Gianna. Thank you, Chris. Now, Otávio.
Thanks a lot, Gianna, for this really rich talk. I have actually a little minor quibble about just the argument that you noted about, well, how could Planck wins the Nobel Prize for something he hasn't done? Well, it would not have been the first time. Right? As we all know, the ways in which the academy describes accomplishments of physicists are not always accurate, right? I'll give you another example. In 1986, Roren and Binnig won the Nobel Prize in Physics for the creation of the atomic force microscope. And in the description of the prize, it says, well, now we can see atoms. But of course, we cannot see atoms with those microscopes, right? Atoms are too big, right? The tip of the microscope is in the size of an atom, so you cannot possibly resolve an atom, right? So, for that reason, I think I wouldn't put much weight at all on that. Of course, their story is more complicated, and you're getting into the nitty-gritty details that need to be placed. But that one, I would just say, look, we can do without that.
Okay, I see. Good point. I mean, this is just a way to further suggest. I'm trying to point out from several directions to suggest that, see, there's something amiss in this story, and here's one indication of it. Right. One of the reasons people believe that Planck did what he did, that he began the quantum revolution, is, well, he won the Nobel Prize for that, right? But yeah, for sure. Thank you, Otávio.
Sure.